So we're looking at University of Physics 14th edition by Young and Freeman, Chapter 5, Bridging Problem, piece of mass in a rotating cone. So here is the problem, the bridging problem at the end of the chapter. And we have a piece of mass resting inside a rotating cone. And so the question, the problem asks for two things. A, the maximum value for the period and the minimum value of the period for the piece of mass to rotate affixed to the cone. Okay, so now we're going to look at the chapter 5 bridging problem written out here. So the drawing from that problem is redrawn here. And so we have the mass, and we're going to look at the different forces acting on the mass as it rotates about together with the cone. So the question for this problem so what are A, the maximum value for the period, and B, the minimum value of the period T for the mass to go together with the cone. So what's the holding the cone, the mass on the cone? And so we know that that's going to be the force of friction. However, for this particular problem, depending on the maximum period or the minimum period, the force of friction is going to change direction. So looking at one here, so what is the direction of the friction force when the cone is rotating as slowly as possible, so that the period t has a maximum value, so t max. In this case, if the rotating too fast, part A, then the piece of mass would go out of the cone, and so therefore there will not be enough normal force to keep it within the cone to sustain the centripetal acceleration. For the other case, if rotating too slow, then we don't have enough vertical component of the normal force to counter the weight, and thus the piece of mass would slide down the cone. So here's a free body diagram for the case with the friction force upward from toward the opening of the cone. So and we see that here we have the normal force, and it's the horizontal component of the normal force that is responsible for the centripetal acceleration. And we also see that the force of friction here also has a component toward the left, and is this leftward component of the friction force together with the normal force that will contribute to the centripetal acceleration. And so here we see that the friction force and the normal force, they're not in the same direction. So therefore here we would have a smaller velocity, because after all, it's the net force, that is the sum of the two forces, component of friction in the horizontal direction and a normal force in the horizontal direction, that will contribute to the centripetal acceleration. So if we have a small centripetal force, that means we're going to have a small speed and thus a large period.